in that case, we're going to start with a lecture on MRI. And basically, the lecture has two parts. One is just basic MRI intro. And then after that, we will talk about open MRI and different developments in the field of reproducible, open, transparent MRI. But that will be more, geared towards the case studies that you will do next week. So for now, the first hour or so, it will just be a general MRI intro. And let me just start by sharing my screen. Can everybody see my screen? Give
Mm-hmm.
me a thumbs up. Yeah. All right. So, as you're aware, this is the field in which I do my research, and it's kind of a double-edged sword because sometimes I can go into tangents and try to explain little details, but I try to keep it uh, high level enough. And if you have any questions, I'm happy to go into more detail. But this first part should just really make you comfortable about the main concepts behind MRI. And I usually start this lecture by telling you how I first learned about MRI. And it was by taking an exam in 1998 from a physics teacher who was teaching introductory physics at Stanford. And this was the most original exam I had ever taken because basically the exam had some questions that were, regular problems. And then it had a research problem that we were supposed to address. And the point of that second part, the essay, was to pick something that we find personally interesting. And one of those options for what we could be covering was what is nuclear magnetic resonance and magnetic resonance imaging. And basically, it told us how to do some research on the work that was done at Stanford and referred us to a couple of books that were interesting to read. And then a couple of years back, I actually found that midterm, and these are just some scans. I will just read the text because it is really the first time I got excited by technology. And I started out by saying that due to the fact that magnetic fields easily penetrate non-magnetic materials, it is possible to map the interior of a body using nuclear magnetic resonance NMR. The physical principles behind magnetic resonance imaging, MRI, are complex and include paramagnetism, Faraday's law, quantum mechanics, Fourier transforms. Uh, I think that was the most appealing part about MRI. It's a very interdisciplinary topic. And basically, whatever field you're studying, there is an aspect of it that is related to MRI. Here's the basic concept, or at least the level of my understanding back when I was 19 years old. Basically, in MRI, low frequency radio waves penetrate the tissue and reflect back off magnetized spins within the object. By measuring the signal produced by this process, it is possible to map the inside of the tissue observed. And then I broke a rule. I went for 10 pages, even though the essay asked me to never go over 5 pages. And I said, what is outlined here are just the most basic physical principles underlying MRI. The rest was beyond my power of understanding. So, these are the kinds of things that I try to teach you now. When we have a limit on length, do not go over. But also, I think it's nice to kind of go back to this moment and realize that it has really shaped the rest of my career, meaning the next quarter of a century, the next 25 years. So let's talk about MRI in very kind of in terms of impact. First, there's tons of Nobel Prizes that have been given to MRI. Some to physicists, starting all the way back to 1944 with Isaac Rabi. Then a couple of Nobel Prizes given to Stanford and Berkeley scientists, Felix Bloch and Edward Purcell. And then in the 80s, Bloomberg and Ramsey. Each of these developed some fundamental MRI property that was then exploited to create clinical MRI scanners. But then there's also the Nobel Prizes in chemistry. And in particular, there's Richard Ernst and Kurt Wuttrich. Those awards came a little bit later, but they were basically for developments that had to do with NMR, nuclear magnetic resonance. Back when we were still not doing images, we were only kind of studying the spectroscopic makeup of molecules. And then finally came the Nobel Prize in Medicine in 2003 to Paul Lauterbur and Peter Mansfield, sorry, uh, that basically said, and now finally this technology is used in the clinics, and it has really revolutionized the way that we look at the human body. So these are the roots of MRI, and they're pretty deep and they're pretty remarkable. And then these are the fruits, different kinds of imaging techniques, some of them having to do with imaging the body, in particular the brain. MRI has the biggest applications in neuroimaging. But also, there's some applications to the study of geology, to look at the structure of soils, to look at different kinds of ores or oil that is available in the soil. Some people are actually using MRI to study economics. They look at the way your brain reacts to commercials, for example. There's even a book about it, Biology, where they try to analyze the way that you are reacting to different kinds of stimuli, and they're trying to use that up to, make you buy more things. Um, and then there's also the study of something more abstract, which is how do the networks in the brain work? How do different parts of the brain communicate with each other? And each of these has different various applications, and we'll touch on some of them. But bottom line, it's an exciting technology, it's a safe technology, and that's why it has really revolutionized healthcare and neuroscience. So let me just tell you a little bit about the basics of MRI. Uh, Before taking this course, you've probably seen an MRI machine that kind of looks like this. You know, plastic, very difficult to differentiate between an MRI machine and a CT machine. They look very similar. And then there is this black box, and then you acquire some data. The data goes through a black box, and out comes a human brain. But in reality, these uh, are a little bit more complex. And in particular, after this course, you will know that an MRI scanner is actually very bare bones apparatus. It has lots of metal, lots of wood. This is actually the MRI scanner on which I did my PhD. It's very old. It's from 1989. And recently it has actually been decommissioned. So now we will have a different scanner at Stanford. But this one has done some pretty remarkable discoveries over the course of more than 30 years. And then if you want to see how you decommission a scanner, this is an image. It's pretty fun. Basically, the one thing that's scary about MRIs is that if you go in with metal, the metal will get yanked and it will go straight into the isocenter of the scanner. So this is a scanner that was about to be destroyed. So what did they do? They took a metal bottle and they started approaching it. And at some point, when it approached here towards the center, all of a sudden you will see what happens. So you see, there's nothing really happening until you get very close to the center, very close to the isocenter, the bore here. And imagine if there's a subject being scanned there. That subject is now dead. And turns out there's been a lot of incidents like this. As a matter of fact, there's been a couple of murders happening in MRI suites because often a politician goes in and their bodyguard comes in with a loaded gun and the gun flies out and shoots somebody. And it's happened more than once. There's also the issue of you walking in with bobby pins or any kind of, metal objects. And that's why we have to check you for metal before you go in. This is the most dangerous aspect of MRI, projectiles that can really hurt you, especially they can hurt the person who's lying in the center of the MRI machine. And then there is the whole acquisition part, where basically the MRI scanner is just a giant Fourier transform taking machine. And I teach about the Fourier transform. I love the Fourier transform. And I feel that if you understand the Fourier transform in the context of MRI, then you really understand the technology. And finally, there's all these different kinds of reconstruction tools. And you don't only get an image of the brain, you can get different kinds of things. You can get tractography, which is different ways that parts of the brain connect to each other. You can isolate the most myelinated fibers. You can actually look at the amount of myelin that you have in the brain. So all of these are different kinds of applications that we'll touch on a little bit today, but it's space is too short to tell you all the different ways in which MRI is useful. Now, before we do that, I just want to kind of orient you and explain to you how MRI images are interpreted. And the way we're going to do this is by just looking at some fruits and vegetables. So let's start with this one. Anybody know what is imaged with MRI here? Shout it out because I'm not reading the notes. It's a fruit.
A banana?
Yeah, or 6 bananas in this case.
Oh, yeah.
Yeah, so that's, something that hopefully orients you how we look at MRI images. We're basically doing cross sections, but we're not cutting through the fruit. This is all, uh, uh, a whole, bucket of bananas that's just imaged, and this would be kind of the equivalent of how we're looking at it, except we're not really cutting it. What about this?
A tomato?
Yeah, who said it? Jane?
Yes.
Yeah, that's tomato. You might have seen this, so I don't know if you count, but thanks for
Yes,
breaking the ice.
yes.
What about this one? This one's really tough. In my country, we call it blue tomato.
A pear,
Nobody?
maybe?
Mushroom?
Oh.
Pear or mushroom? No, it's an eggplant, or what's the French word for eggplant?
Aubergine.
Aubergine. There you go. Thank you. All right. What about this one? This one should be easy.
Orange.
Yeah, it's an orange. What about this one? It's large and round. That's a watermelon. What about this one?
An
Onion?
That's an onion.
Onion.
Ah.
Yeah, there you go. Yeah, that's an onion. And that one is a human brain. Interesting thing to notice. See how the nose of this person kind of comes around to sniff the back? See nose right there? Everybody see that? So that is called aliasing, and it's a problem in MRI. And I'm going to explain to you how that happens. So yeah, I tried to find something appropriate. I don't know if you've seen this exhibit, but there's this pathologist that's been slicing and dicing human bodies and human brains. This exhibit comes to Montreal every now and then. So yep, there you go. That's the equivalent of a sliced fruit. And then this here is basically an entire body. That is a combination of computer tomography, CT, MRI, and histology. And now we're going through the legs, and now these are going to be the feet. And then we're going straight from the head, neck, shoulders, lungs here, liver, intestines, pelvis, and now we're going on to the legs. It's also possible to image moving body parts, and in particular, this is an MRI of a beating heart. Now, as I told you, MRI is safe. That's why it's possible to do MRI studies on healthy people. There's no dangers. That being said, MRI is slow. So to be able to capture a beating heart, these images are really sophisticated because the heart beats fast, and MRI usually takes its time with acquiring images. But it's pretty amazing that we can also do this, even though for cardiac imaging, there's all other kinds of applications. But MRI is the safe one. MRI is the one that doesn't really cause any side effects.
I have a question about
Yes.
the last slide, the human body.
Mm-hmm.
Are the colors like artificial?
So I mean, colors are always artificial in the sense of, you can do a stain and then you can reinterpret that stain in different shades of gray or shades of red in this case. Honestly, I'm not so sure what the staining used here was. This one, you can look it up. It's actually the body of a convicted killer who was executed and then donated their body to science. And Honestly, I don't know what kind of staining they did, but in MRI, usually the images are black and white, and then we just give them color to make it easy to interpret. Any other
Right.
questions about what images that you saw? What do you
Sorry?
think? How long is an MRI scan? Do you know?
When I have been some exams, it was like 15, 20 minutes that I had to
Yeah.
stay, usually.
So it depends on, the resolution you want to get. It depends on what you're actually looking at, but you could get a very nice anatomical image in about 10 to 15 minutes. And then depending on, the protocols, people sometimes add other things. Scans can go up to an hour, but usually 15 minutes is optimal to get a good image. But in MRI, there is this trade-off between how long you scan and how good the resolution of your image is. So sometimes I've been in the scanner for many, many hours. I've been in the scanner for like 3, 4 hours to get some very high resolution images of my skin. And I mean, I'm fortunate that I can just fall asleep. So for me, sitting in an MRI scanner is not a problem. But if you're claustrophobic, then those can be some very uncomfortable 10 to 15 minutes.
But when
But
you
then,
say that you're taking like images with the movement and it's like 15 to 10 minutes, how can we manage it? Because
Yeah.
like a beating heart is not 10 to 15 minutes. So how do we
Exactly.
reduce
No,
the
it's
time?
seconds. Yeah. Yeah. So what we do in that case, it's something called gating. Basically, we use an ECG trigger to find out how to locate the exact time point when the heart starts to beat or, systole, diastole, different kinds of phases of the heartbeat. And then what you do is you average over a lot of the same time points. The trigger says image now, and then you image. So what you're seeing is not technically the, single heartbeat. It's an average over many heartbeats, but always acquired at exact same time, in which case it appears to be a single heartbeat. So it's a trick. You can imagine that unless the heartbeat is regular, it's not going to work. But most of the time, heartbeat is regular, and that's how we manage to make those images. So usually we use them to see how much the ventricles expand or contract, and that kind of thing is independent of the regularity of the heartbeat. Any other questions? All right, so let me tell you about the hardware first, and then we're going to talk a little bit about the processing and the physics behind it. So, as the name implies, MRI stands for magnetic resonance imaging, and the most important part is the magnetic part. The instrumentation consists of many magnets, and the three that are most important is the main magnet. That one is on the order of Tesla. So it's very, very strong and very expensive. Most of the time, this main magnet is superconducting. And in order to be able to have superconduction, do you know what is necessary?
very low temperature.
You need very low temperatures. So basically, you get down to 3, 4 Kelvin, and it's not easy to accomplish those temperatures. Do you know how we do it? How we get to temperatures that low?
Think helium is used?
Yeah, we use helium. And helium is in short supply, so we're running out of helium on Earth, so scanners have gotten more and more efficient with the helium so that it doesn't boil over. Turns out that there's been huge talk about superconduction at room temperature. And a couple of years, like a year ago, we thought that, oh, now we actually have that superconductor at room temperature. Turns out it didn't really replicate. It was not a good result. But you can imagine what that will do to medical imaging if we could get superconductors at low temperatures. The way they are now, these scanners are expensive. So depending on the strength of the field, the price is usually on the order of millions of dollars. So a 3 Tesla MRI scanner costs about $3 million to purchase the scanner. And then on top of it, every year you pay the manufacturer about $300,000 for the maintenance, meaning checking for helium, software upgrades, any kind of repairs that need to be done. So it's a very, very expensive machine, primarily because of the strong magnetic field. But then there's other magnetic fields. In particular, there's something called gradient coils, and those are kind of on the inside of the bore. So you have the big magnet that's on the outside, And then on the inside, you have the gradient coils. Those are the ones that are not very strong. They change the field just a little bit, and they're kind of like speaker coils. You know, they're just tightly wound coils that vibrate when you change electricity through them. And that's why for anybody that's had an MRI, that's why you hear this sound that sounds like just, you know, metal grinding on each other. It's basically loudspeakers that produce sounds as the current oscillates through them. And finally, there's another coil called the radio frequency coil. And that one is an electromagnetic field that's usually applied for very brief spurts of time. The strength of those fields is on the order of Gauss. And those are really not expensive. Those are really antennas that have to go in and excite the body. So regarding the breakdown of where everything is, how everything is being used, the radio frequency coil and the gradient coils, those can be replaced. But the main magnet, if it quenches, meaning if the helium evaporates, then you can no longer repair the scanner. It's pretty much ready for the trash. Re-ramping a magnet, it's really expensive and really difficult. So what you do is you get it up to a certain field strength, 1.5 Tesla or 3 Tesla, and then you leave it there. So the MRI scanner is always on. We never turn it off, which means you can use it 24 hours a day. It's not losing more electricity. It's actually very efficient once you get it up to the necessary field strength. And then inside here, you have the cylinder bore. This is where you insert the patient, and this is how you do the imaging. However, that's not the only geometry that works. You can also have different kinds of open geometries. For example, you can have an MRI scanner where the field is between these two plates here, or you can have something that's kind of like an interventional MRI scanner where people will actually perform small interventions, operations on you while you're being imaged. Sometimes we have scanners that are upright. Also, sometimes we have scanners that are only for one body part. For example, there's scanners that are head only, extremities only, etc. These are cheaper. Sometimes they're resistive. And recently, there's been some efforts to make magnets, MRI magnets, that are comparable to the field strength of the Earth. They're not very good, but they are cheap, and people are saying maybe that will revolutionize the way that we do healthcare. Just for a sense of scale, 1 Tesla has about 10,000 Gauss, and the Earth's magnetic field is about half a Gauss. So, you know, we're talking field strengths that are about $20,000 stronger, 20,000 times stronger than the strength of the Earth. So about that main magnet, as I said, it's superconducting. It's cooled with liquid helium. It has many, many kilometers of wire. The field strength somewhere between 0.5 and 3 Tesla, but it can go up to 11.7 Tesla for human research. And then there is the issue of shielding, which is when you have such a strong magnetic field, that magnetic field spills over outside of the room where the scanner is. And that could be a problem because if you have a pacemaker, for example, the MRI field will interfere with your pacemaker, and that could kill you. So what we do is we put the MRI scanner in a Faraday cage. The Faraday cage is meant to prevent any field lines from exiting the room, and that's why it's possible to get close to an MRI scanner without causing serious problems for people that have metal in their body. There's also a couple of other fields that we're not going to talk too much about, but you know, there's shimming coils. Those are the coils that ensure that this magnet has exactly 3 Tesla or exactly 1.5 Tesla. It's very important that the magnet is very uniform, because if it is not, you will have different kinds of image distortions, and then it's no good. Your millions have gone to waste. Then there is the field called gradients. These are lower field strengths. They're usually on the order of millitesla per meter. So we're talking about Tesla for the main magnetic field, but then gradients add small linear spatial variation to this B0 field. They're fast switching. You can control them very easily. They operate with high currents, so you need to cool them all the time, and they could cause some bioeffects. Are you aware of some bioeffects of the MRI? Like, has anybody felt something uncomfortable with the MRI? Does anybody know what is peripheral nerve stimulation? So this is an effect where basically you have very fast switching magnetic fields. And because of that changing of the fields, your nerves will react because they react to electricity. So the magnetic fields will induce currents in your nerves and your nerves will jump. Now, that could be a problem if you're actually exciting some parts of your nervous system that are deep inside the body. Fortunately, you're only exciting the periphery, and then it just results as twitching, like little twitches that are not particularly dangerous, they're just uncomfortable. There's another weird thing, which is if you're around an MRI magnet and you shake your head, you will get dizzy. Do you know why that is? So think about what's happening. You are standing in a very strong magnetic field, and you have some conductors in your head. Basically, that's the fluid that you have, the liquid, the cerebrospinal fluid. So as you're shaking your head, you're basically moving a conductor in a magnetic field, so you're inducing a current. That current will affect many of your neurons in your head, in your brain, including the inner ear neurons. So that makes you feel dizzy. There's another interesting thing. Inside the scanner, sometimes you get a metallic taste in your mouth. Can you guess why that is? So basically, you have electricity going through your tongue, and that usually activates receptors that make a weird taste. Now, it's not really easy to determine. It's not salty, it's not sweet. It's just kind of as if you put a battery on your tongue and then you get that metallic taste. But all of these things are actually very tolerable, and they do not prevent us from actually using the MRI scanners. They're known side effects, but so far nobody's died from them. And that's why for about 50 years, MRI has been used, very safe. I myself have gotten scanned hundreds of times. And yeah, if anybody wants to volunteer, we always have some studies. So if you're curious, I'm sure we could arrange for you to be a volunteer for an MRI. Finally, there is the third system, and this one is the one that actually creates the resonance. We'll talk a little bit about that, but it's really just an antenna. And this antenna produces radio frequency fields, meaning fields in the megahertz range, usually about 60 to 120 megahertz. And the amplitude of these fields is in microtesla. So it's about 100,000 times less than the main magnetic field. And these are used for excitation, inversion, and refocusing. So you have the main magnetic field in Tesla, you have the gradients, millitesla, and you have the B1 field, or the radio frequency field, and that one is in microtesla. And somehow these three magnetic fields work with each other to create images of the human body. So how do we receive this signal? Basically, we build coils. The antennas are transmitting signal, and they're also receiving signal. So what we're doing is we're magnetizing your body, and then we're letting that magnetization induce currents. And then we have coils that can receive those currents, and then we can interpret that as just a biological signal. So we have to have amplifiers, demodulators, digitizers, all kinds of circuits that are just necessary to be able to receive an antenna signal. And then we have to make sure that the coil is matched to the size of the object. There's different coils for the head, different coils for the wrist. And then sometimes we combine these coils so that we can create arrays. For example, this here is a coil array, so you can place it on the surface on your chest to image the heart. Or you can have something like this. This one here is a head coil. It has 8 channels. They're organized in a cylinder, and they're good for imaging the head. Breast coil, you see how it has openings for the breasts. Knee coil, where basically you put your leg inside and you can image with a cylinder around your knee. So that's it about the hardware. Any questions about that? As you can imagine, this hardware gets really hot. So the liquid helium is the one that maintains superconductivity, but then we have a water cooling as another layer to make sure that nothing overheats. And we have a very complicated system of maintaining cold head pressure to make sure that the water circulates and never boils over the helium. Srijani, a question?
Yeah, I wanted to ask if quenching is also a part of hardware or it's something else.
No, quenching, sorry, I used it without explaining what it is. Quenching is when the liquid helium boils off. So basically when the temperature goes really high, liquid helium becomes a vapor, a gas. So as long as it's liquid, it stays at about 4 Kelvin. The moment it starts evaporating, the gas expands and then it just blows out. So the
Okay.
quenching is the process of the liquid helium becoming gaseous helium and then evaporating, and then your scanner can no longer maintain superconductivity.
Do you get to recycle it, like convert it back to liquid and then reuse it?
Not really, no. I mean, there's the danger is the opposite, actually. Once this starts coming out, you need to get out of the room because the helium will displace the air. So
Okay.
you don't have time to save the helium. It's gone. You'll just get another bottle. But the problem is that that scanner is probably not reusable. You will have to get a new scanner. Sometimes you will be able to save it depending on whether there's big hardware damage, but a quench is the last thing you want to happen to the MRI scanner. All right. So now let's talk about the physics. And this is where it'll show that I'm an engineer, not a physicist, because I'll be talking in terms that will make physicists cringe. But basically, when you have water, you have hydrogen spins. Turns out that a magnetic spin is a property of every chemical element that has an odd number of protons or neutrons. And in the case of hydrogen, that's simple. It has an odd number of protons, 1. And we treat every hydrogen atom as a small, tiny magnet. It's very wrong to think of it that way. In reality, magnetic spin is a quantum mechanical phenomenon, and these magnets are never oriented diagonally. They're always oriented parallel to the field. Except, as engineers, we try to simplify things. So rather than say we have spins up and spins down, and a magnetic field makes all the spins slightly more preferential to the up direction, we say, you know what? Each of these spins are little magnets. And when you put them in a magnetic field, what they will do is they will try to slightly align with the magnetic field, just like that. Okay? So it's not very noticeable. It's parts per million, the effect, but it does generate precession where each of these magnetic vectors, each of these magnetic spins, precess around the B0 field, and they precess at a frequency called omega, which is the product of the gyromagnetic ratio and the main magnetic field. So basically, for every Tesla of a main magnetic field you have, you will be precessing at a frequency of 42.58 megahertz. So if you have a field of 1.5 Tesla, you're operating at 64 megahertz. If you have a field of 3 Tesla, you're operating at 128 megahertz. So this gyromagnetic ratio determines that the higher the field strength, the higher the frequency at which these spins precess. And these spins will combine to create a net magnetization. In this case, the net magnetization will be aligned parallel to the main magnetic field B0. So, strong magnetic field B0, strong net magnetization. And imagine that here we have basically a glass of water, and we have just magnetized the water. Now, nothing exciting happens until we start manipulating this magnetization. At the moment, the magnetization is just parallel, stays there, your body's magnetized, but you cannot make an image that way. Instead, what you do is you use this third field, the RF field, and you apply an RF pulse, a radio frequency pulse, on resonance, meaning at the frequency determined by the precession of the spins. So if you're at 1.5 Tesla, your precession is 64 megahertz, you apply a radio frequency pulse at exactly 64 megahertz. What does that do? It takes the magnetization and it tips it into the transverse plane. So we used to be perpendicular with the B0 field, and now we are going in the transverse plane. Now we're perpendicular to the B0. And if we turn off this pulse, the magnetization will return to normal. So basically what I'm doing is I'm turning on a pulse, exciting the magnetization, putting it into the transverse plane, and then turning it off so that you have two mechanisms, a mechanism called T2 relaxation that makes the magnetization disappear in the transverse plane. This is called the transverse plane. And then you have T1 relaxation, which makes the magnetization recover in the longitudinal direction. And if you repeat this long enough, that is actually the basic of something called a RF pulse sequence. So these MRI pulse sequences are protocols that you apply so that you're able to generate a good image of your body. What do? You excite, and then you let the magnetization recover and relax. And sorry, I just want to minimize the screen here so I can show you. So basically you excite, and then you have the transverse magnetization, which is decaying. And then you have the longitudinal magnetization, which is parallel to the B0, that is actually recovering. And you do this multiple times, and you get an MRI pulse sequence. But how do you actually generate contrast? For example, this is just a single glass of water. Nothing's happened here. We've just managed to excite it, but it's all full of water, and there's not going to be any contrast in our images. But imagine that we have two different tissues. One may be a glass of water, and the other may be a jar of fat, for example. In that case, when you excite them, both the fat and the water will get excited. But then when you turn off the magnetization, the rates of relaxation will be very different. For example, the red one will recover and relax way faster than the blue. So this is a way of generating contrast between two different tissue types. And you can see that in the pulse sequence diagram as well, because you excite, but then you have the blue, which is decaying slightly slower. You have the red that is decaying faster. And you also have the blue that is recovering slower and the red that is recovering faster. So depending on where you would like to explore this phenomenon, you see that you're able to get some good contrast between the blue and the red tissue. And we actually exploit that. And depending on where we do the imaging, we can actually create different kinds of contrasts with MRI. And this is what's very nice about it, that MRI is a very flexible imaging modality, where if you want to focus on certain body parts, you can tailor the sequence to give you those body parts. This image here, it's called a T1 weighted image. And you see that in a T1 weighted image, the ventricles, which is the place where you have liquid with the cerebrospinal fluid, those appear dark. Whereas the white matter here appears bright. And then the gray matter is somewhere in between. You see the gray matter here in this sulci that has T1 values that are kind of between the liquid and between the white matter. Usually for my students, I ask them to develop intuition about this, but for you, I'm just going to try to interpret, these T1 values. In the ventricles, we have liquid. The liquid has very long T1 values on the order of 2, 3, maybe even 5 seconds. So because these T1 times are very long, the magnetization takes a long time to recover. And because the magnetization takes a very long time to recover, because that is the T1 time, that is the recovery of the MZ, of the longitudinal magnetization, that means these magnets have no time to recover and they will appear dark on a T1 weighted image. But there is also T2 contrast. So T2 contrast is concerned with the transverse magnetization, which is the MXY. And there you will see that the water, the ventricles, actually appear bright. The reason they appear bright is because water also has a very long T2 time. Now, if the T2 time is long, then for the magnetization, it takes a very long time for it to decay. So it's kind of more like the blue over here. And therefore, we'll be able to image it and get some signal. Unlike the water, the gray and the white matter are slightly darker. That is because they have shorter T2 times. So this mechanism, it's difficult to explain right away, and I don't expect you to have it intuitively right now, but you see how we can choose where we image and choose whether we're working more with the longitudinal magnetization or with the transverse magnetization to create different kinds of contrast. And this is very rare for medical imaging, that you can actually make any part of the body be either bright or dark, depending on what you're interested in looking at. Any questions about that, about the way that we generate contrast in an MRI? Okay. In that case, let's make it a little bit more complicated. And this is the part that's related to the work that I do. Basically, there's conventional and quantitative magnetic resonance. Conventional magnetic resonance, it's the kind of stuff that's used in the clinic. It's probably, I would say, 95% of all MRI scans ever done. And in addition to T1 and T2, there's many other contrast mechanisms in MRI. So when you're doing an image, what you're actually doing is you're taking a spoonful of an alphabet soup of different contrast mechanisms. You can get some T1 weighting, you can get some T2 weighting. You can also get some proton density weighting, meaning how many protons are there in the tissue. You can also get something called magnetization transfer weighting, and each of these have different properties and they give you different kinds of specificity to tissue. If you want to image water, you will do T1 imaging. If you want to image myelin, you will do MT imaging. And physicists develop all kinds of different contrast mechanisms in MRI to be specific to what you want to show a picture of. But in conventional MRI, images are just regular numbers, digital photos, where each pixel has a certain value, but those values are not connected to units. So you really don't know what you're measuring. You're just saying, well, in this photo, the ventricles are dark and white matter is bright. And if there is a tumor, I expect the tumor to have different contrast, and I will be able to capture it. The problem with that is it's really difficult to do any kind of quantitative analysis because it depends on when you did the scan, where you did the scan. Longitudinally, it's difficult to follow. Comparing patients is also very difficult. Unlike conventional MRI, there is something called quantitative magnetic resonance imaging. And in quantitative magnetic resonance imaging, all of these contrast mechanisms are nicely compartmentalized. They're kind of like little compartments in a Japanese bento box. So you could take a look at the T1 compartment right here, and you can say, let's take a look at the T1 parameter. This image is also a T1 image, except here the T1 value has units. And you could take a look in the ventricles and you could say the T1 value in the ventricles is 3 seconds. And the T1 value in the white matter of the brain right here is about 800 milliseconds. And this enables you to perform the same measurement everywhere, all the time. And you can imagine that with the development of AI algorithms and all of these kind of automatic analysis of images, this kind of quantitative MRI approach would be very useful. So I would like to spend some time on how we can measure these parameters, how we can quantify them, and then we're going to talk a little bit about the way that we actually create the images, which has to do with the Fourier transform. So for this contrast intuition.
I had a question
Yeah, please
about
go
the
ahead.
contrast.
Mhm.
I was wondering when you would want to use T1 and T2 contrast based on the application.
So usually you use T1 if you want to look at water content. So for example, imagine that you have inflammation in your brain or edema, then you would want to look at a T1 image. On the other hand, if you would like to take a look at myelin content and lesions and loss of white matter, then you would like to take a look at T2 images. And in between, there's many different kinds of contrasts. There's also a combination of T1 and T2. In reality, in the clinic, the doctors will do a T1 and a T2, and basically they will look at them together to make sense of the image. Most of the time, these are the two main acquisitions, a T1 weighted and a T2 weighted, and then sometimes they may add something called diffusion imaging or magnetization transfer or different kinds of scans.
Okay.
All right, so this intuition here comes from my academic grandfather, meaning the PhD supervisor of my PhD supervisor. His name is Al Makovsky. He is 94 years old, and he's still going strong. We just got to see him a couple of months ago at the celebration of the MRI scanner that got decommissioned at Stanford. And basically he says, imagine that you want to measure how much water there is inside this water container. Well, you don't know because it's closed. So what you need to do is you need to flush the container. So first the container fills up with water. That is the main magnetic field. How much water? I don't know. let me flush it. The moment you flush it, all of the liquid drains from the box inside this stool, or what do you call this? Inside this container. Except here, the water is actually flushed and you're able to measure how much water there is. Except there is this one problem, which is the water will drain out. It will not stay in this plate for too long. So the water goes away, and then it charges once again inside the closed container. So you do this multiple times, and you're able to measure what are the T2 and the T1 constants of the water that you're flushing. And if you have very simple modeling, you can say the MZ, the longitudinal magnetization, meaning the water in the closed container, that one is recovering with a time constant T1, whereas the water from the bottom container is draining with a time constant T2. And you cannot measure MZ. The only thing you can measure is you can measure MXY, and then you can make inferences about MZ because MZ is closed. In reality, MZ is perpendicular to the B0 field, so we do not have a good mechanism of measuring it because B0 overrides everything. But in the transverse plane, that's completely orthogonal to B0, and we will be able to make some measurements, and you will see how we will do that. So these are the formulas, and you could actually have it with two different flushing mechanisms, one that has more water, the other that has less water. You flush, and the T2 and the T1 times are going to be different, so you'll be able to create contrast and differentiate water from white matter, for example. All right, so now I want to show you how these magnetizations are actually happening. You have a field in the transverse plane. This is the RF field, the one that is on resonance. And if you apply it, then the magnetization that is actually aligned with the Z field, that is parallel, will slowly tip from the longitudinal axis to the transverse plane. So we've been able to take this magnetization, which is parallel to the strong field, and to tip it into the transverse plane because that's where we will be doing our measurements. Now, as many geometric problems, often you can change the coordinate system. So you can either work in this coordinate system where everything is spinning and it's spinning at the resonance frequency, or you can say, imagine that the frame, the rotating frame, is actually spinning, in which case it's much simpler because basically what you're doing is you're just tipping the magnetization from the longitudinal axis into the transverse plane. So most of the time we analyze things in the rotating frame, which is really easy to do because you just demodulate the signal, and that's a simple problem done in radio the whole time, but it makes the analysis a little bit simpler. Now you could take a look at the vectors from the top. So what you do is you excite the magnetization into the transverse plane, and then you let it relax. And as it relaxes, it spirals back in, becomes 0 in the transverse plane, and at the same time, it recovers in the longitudinal axis. And I don't see your faces here, so I'm not really sure how everybody is, getting this. But are there any questions about the geometry here? Are you able to picture this magnetization that starts parallel, tips into the transverse plane, rotates, and while it rotates, it actually spirals in so that it becomes 0? How's everybody doing? I see some nods. Looks like everything's okay. Perfect. Let me just continue then. Okay. Now, we are able to measure this T1 parameter. And the way that we do it is we tip the magnetization, but we do not tip it into the transverse plane. We actually tip it all the way down so that it goes from positive M0 to negative M0. And then we wait for it to recover. So I've tipped it from this orientation all the way down. And now the magnetization needs to slowly but surely get back to the regular equilibrium value of M0. While it is doing that, it's crossing through many points. So it will cross through 0 here, and it will cross through a non-zero value here. So at some point, I will decide, you know what? I will wait for the magnetization to grow this much, and then I will tip it into the transverse plane. And then once I tip it into the transverse plane, then I can actually get how much magnetization was there. So depending on how I time this, I can find out what is the maximum amount of the magnetization, and I can do this measurement at many different points along the recovery curve. I excite here at TIN, I excite here at TIN plus 1, I excite here at TI1, and then I'm able to really trace this exponential curve and be able to measure how much magnetization there is at different points in time. And this is one way to measure the T1 value. There's other sequences that kind of do similar things. You know, they tip the magnetization a little bit, wait for it to recover, and then you try to model that. There's equations that will tell you this is the formula, this is what guides the T1 recovery, and this is how you calculate the T1 time. Something very similar happens with T2 mapping. With T2 mapping, what you're doing is you're basically tipping the magnetization into the transverse plane. And then there is the process in which the magnetization is disappearing. And what you're doing is you're waiting for the magnetization to disappear, but then you're actually recovering it with something called inversion pulse. And you're able to measure the magnetization at many different time points. And if you do that many times, you will be able to trace out the exponential line, and you have enough data points, you could actually measure the T2 component, and you will be able to perform T2 mapping. The most important thing in this T2 mapping sequence is a protocol called spin echo. Now, understanding the spin echo is a little bit hard because what's happening is you have excited the magnetization into the transverse plane. But then there is inhomogeneity, a variability in the magnetic field that makes different kinds of magnetic vectors process at slightly different frequencies. So you tip in the transverse plane, and instead of waiting for the T2 recovery, which basically destroys the magnetization, you end up with lots of magnetic spins that are just starting to slowly drift apart. And as they drift apart, you will lose your magnetization. But because they're drifting apart, what you can do is you can actually completely flip them by a 180 pulse. So they go from here to here. And if they were dephasing in a counterclockwise direction, then they will slowly start to dephase in a clockwise direction. And if they were dephasing in a clockwise direction, they will slowly start phasing in with the counterclockwise direction. So slowly you're able to recover this magnetization that you have lost. And this discovery of the spin echo is probably one of the biggest discoveries in MRI. I will try to illustrate it for you. Basically, imagine that you have magnetization vectors that are from water, from fat, from iron, from all kinds of components, and they process at slightly different frequencies. Srijani, there's a question?
Yeah, I wanted to clarify if this is like a compensating mechanism.
So it is, absolutely. Basically, what's happening is the B0 field, the main magnetic field, is never perfectly uniform. And even if it was, there's different kinds of spins in the body. So maybe the hydrogen atoms are perfectly tuned to the resonant frequency, but there's other isochromets, other components that will process at slightly different frequencies. So to be able to compensate for this, take a look at this video. Basically, you have the hydrogen, the iron doing it differently, but then you tip everything into the transverse plane by 180 degrees, and then they manage to come together. And once they come together, then you can actually image right here, and you can find out what is the actual T2 constant. So this dephasing, that's not due to T2. That's dephasing due to different resonant frequencies. But then, after that, you're able to recover them, put them together, and then you have compensated for this dispersion, and you have been able to observe the real T2 decay time. Does that make sense?
Okay. The other thing I wanted to ask is, do we record all ions or just protons while we do an MRI?
Well, different scanners are tuned to different chemical compounds. Most MRI works with water and hydrogen. So basically you have hydrogen and other components too. but most of the time we tune to the hydrogen in water. Turns out that the hydrogen in fat is at a slightly different frequency. The hydrogen in fat is about 220 hertz off resonance. So you still work with hydrogen, but the fat hydrogen processes at a slightly different frequency. You could be working with other atoms. You could be working with phosphorus, for example, because again, it's phosphorus 31, so it has a magnetic spin. So different kinds of compounds will have different kinds of properties, and you can have MRI scanners that can tune to the different frequencies, but most of the time we're working with hydrogen, and hydrogen in water is the one that gives us the strongest signal.
Okay.
All right. So now that I've shown you how we can do this T2 mapping, really what you can do is just kind of continue to tip. Rather than do it once and then wait and do the experiment again, what you can do is you apply an inversion excitation pulse. Just a second, Maud, I'll get to you. And then you wait for a little bit, and then you tip with a pi pulse, and then you read out. Maud, go ahead.
Yeah, it was just a question about before. I wonder, like, what's the difference between an MRI that doesn't take into account this spin thing and an MRI that does take that into account? Is it about resolution? Is it like a condition, a sine qua non condition under which the MRI works? I'm not sure about the impacts.
Yeah, so basically your question is, doesn't take into account this dispersion? I didn't hear that word.
Sorry, my
The
question
dispersion of the
is,
spins.
like this, yeah, this spin, like
Yeah.
what you just described before, is it
Yeah.
a new technology or is it a
Yeah,
condition
no.
that an MRI
It's actually a very old technology, because without it, you would just lose the signal in the transverse plane right away. And then
Okay.
you would need to image so fast that your images are never going to have good signal to noise ratio.
Okay, I
So in
understand.
reality, there are ways of imaging without this without this compensation mechanism. And those are really good if you want to image something that has very short T2 values. For example, if you want to directly imaging myelin, then you don't have time for this kind of spinning. But then your signal to noise ratio is going to be very, very short, because you don't have a spin echo. You just have something called a free induction decay. Back in the day, that was good enough, especially when people were not doing imaging, but they were just characterizing chemical compounds, because you could repeat it over and over and over, and you can average. But when you try to make an image of the brain, then you're limited by how long the person can stay in, and that's where this spin echo comes into play. Now, if you cannot refocus well, there will be artifacts in the image. And I assume you have a follow-up question, because your hand is still raised?
Oh, no, I just forgot to put it back
Yeah,
away.
okay.
But thanks, it's clear.
Yeah.
Thank you.
Okay, good. So basically, this is what you're doing. Basically, there's T2 decay that looks like this. That's what you want to measure. But then there is this issue called T2 star decay that I just showed you how it happens, and it's really, really fast. So if you want to not account for this T2 star decay, you have to image here. But the hardware makes that very difficult. Otherwise, you refocus, you use your pi pulses to reverse the dephasing, and then you get back here, and now you're able to only monitor the T2 decay and measure here. And then you excite again, things will go down with T2 star, you'll be able to recover them, and now you're here, and you're able to measure another point on the T2 decay curve. You measure a couple of those points, you fit an exponential, and you have a very good T2 map. Something very similar happens with the T1 inversion recovery. Basically, what you do is you image at different times. You get different kinds of image quality here. You see how it starts out by being very dark. Then you get more signal, and finally more signal. And then you try to fit an exponential. And that exponential will give you values for the T1 in different parts of the brain. And very similar with the T2 mapping. Same idea. You measure here, then you measure here, then you measure here, then you measure here. And then you're able to map different kinds of tissues. Here you have the cerebral spinal fluid. As I told you, it has a very long T2 value. That's why it appears as bright. And then you have the gray matter and the white matter that have slightly different T2 values, but as you see, the contrast between them is not very strong. So even here in the images, you see that, yeah, I could tell that this is gray matter and this is white matter, but it's not very remarkable. The big difference is between the gray and white matter and the liquid that is in the brain. So then you get a T2 map where each of the parameters has a corresponding unit. The unit is in seconds, and you're able to compare different kinds of voxels, different kinds of points in the brain based on their T1 and their T2 values. So that's it about the contrast. Does that make sense? Feel free to ask me questions. All right, so then we're going to go to case space, meaning the Fourier transform space. Now, these slides are slides that I made for my PhD defense, except I never used them. I got so obsessed with making them right that I didn't realize that they take too much time and they weren't really related to the work that I was doing for my PhD. So it took me a while to figure that out, but I really wanted to show them. And fortunately, I've been showing them ever since, because every time I teach about the Fourier transform, I think they're the most intuitive way to understand how MRI makes images. Before I do that, I just want to give you a hand-wavy argument for the way that these images are built, which is, you know how you have the magnetization vectors and they precess at the frequency that's proportional to the main magnetic field. So if I put my whole body in a 3 Tesla scanner, all of the spins in my body will precess at 128 megahertz. But now imagine that I make the left part of my body precess at a slightly different frequency than the right part of my body. How much? A couple of hertz. So over here, I'm precessing at 128 megahertz plus 10 hertz. And over here, I'm precessing at 128 megahertz minus 10 hertz. Now, all of a sudden, I have a way of mapping a location in my body to a very specific frequency. So I have managed to make certain parts of my body precess at a slightly higher frequency and other parts of my body precess at a slightly lower frequency. But every time you have that kind of mapping of space to frequency, this is where the Fourier transform comes in, and it's very useful. Now, I'm very curious how many of you have seen the Fourier transform, taken a class, done at least a couple of hours with the Fourier transform. Okay, looks like most of you, but not everybody. So I will try to explain it without worrying too much about the theory of the Fourier transforms. And we're going to do it this way. Remember, we had 2 tissues, and they're precessing around the main magnetic field. Now you are looking at it from the front. The field is this way, and you're looking at them this way. So they're precessing around the B0 field. What we will do now is we will flip, and we will start looking from the top. So as I told you, we have the Larmor frequency, and that Larmor frequency is proportional to the main magnetic field with a gyromagnetic ratio. So now let's take a look from the top. Okay, so now your magnetic field is going into the screen, and your magnetization vectors, they've already been excited. We assume there's no decay. They are there, and they're going to precess for a long time. So let's just show that. There you go, they're precessing. Except they are precessing at exactly the same frequency. So instead, what we want to do is we want to apply a gradient. As we said, the gradient is a couple of a couple of Gauss. So now the red one will precess faster and the blue one will precess slower. And now we have these magnetization vectors that are turning. But every time you have a magnetization vector that is turning, that is changing the flux. You put an antenna, and that antenna will be picking up different signals from the 2 different magnetization vectors. So here's an antenna, and it is trying to pick up signals from 2 vectors, the red one and the blue one. For the antenna doesn't care that the red one is slightly more to the right and the blue one is slightly more to the left. This is just an electric signal that is arriving from the same body of water or tissue. So the antenna is receiving these 2 signals, the red one and the blue one. The red one is at a higher frequency and higher amplitude. The blue one is at a lower frequency, lower amplitude. But all you're getting is this total signal here that looks just like a jumble of frequencies. And then what you can do is you can take that signal you can take a Fourier transform, and the Fourier transform will tell you which frequencies are present in that signal. In this case, the Fourier transform will tell you, oh yeah, there's a little bit of blue right here at this frequency, and there's a little bit of red right here at this frequency. There's more red than blue. So this is still very hand-wavy, but have you been convinced that by manipulating the center frequency using a gradient, I'm able to map position to frequency? Okay, I'm just looking at, some reactions. How plausible is that? Like I'm just telling you, I make different spins process at a different frequency, and then I have a way of differentiating left from right. Now, we're going to do something way more complicated than that, but the idea is that still we will be preserving this information about which parts of your body process at different frequencies. The main field doesn't change, but we have a gradient that makes certain parts slightly lower frequency and certain parts slightly higher frequency than the resonant frequency. So that's the basis of the Fourier transform. You take different frequencies in one dimension here, so magenta, red, blue, you combine them and you get a waveform. If you work in 2 dimensions, you combine horizontal frequencies, vertical frequencies, diagonal frequencies, and you end up with something that looks remarkably like an image. Not a very interesting image, but you can imagine how combining all of these frequencies can give you pretty much any image you want at this particular resolution. So, how do you make an image of the brain? You just combine a lot of different frequencies. You combine the DC frequency, which gives you kind of the contrast or the total number of energy in your image. And then you add different kinds of frequencies. These ones with variations in the X direction, these ones with variations in the diagonal direction, and these ones with variations in the X direction, but at a slightly higher frequency. Each of these frequencies can be mapped to a position in something we call K-space. K-space in MRI is really just the Fourier transform space. So we have represented each point in the K-space with a particular frequency. Here's the black diagonal, corresponds to this. Here's the blue or the cyan right here, corresponds to the DC value. Here is the orange, corresponds to a variation in X with a pretty low frequency. And here is the dark blue one, and that one is variation in X with a higher frequency. Imagine that we fill up all of this space. Imagine that we get each of these points. And then the only thing we need to do is we need to take an inverse Fourier transform to get an image of the brain. How's everybody with this? Do you have any questions?
I'm just wondering, I know, I'm pretty sure it's just a principle, but do we only like use fixed direction of polarization, or do we like rotate something? Is it like time, like does it vary with time?
Yeah. So basically, we control how we acquire these points, and I will show you how we do that. In general, there's an order to it. So, we go either in a spiral or we go rectangular, but we completely control which points are required at which point in time. Was that your question?
Yeah. I
Okay.
wonder how we do that.
Yeah, so we're getting there. Okay. So now I've told you if I can acquire each of these points, the image of the brain is trivial. Okay. So now we'll see how the gradients control this. Until now, all I told you is the gradients make different parts of your body process at a different frequency. But now what I will show you is how the gradients are very specific in the way that they do that. And these are the slides that took more than a month of my PhD thesis preparations only to never be used in my PhD thesis. So let me try to set it up for you nicely. Imagine that I have a box, and this box has air, black, and then inside the box, there is also another small square that is filled with water. But the box is closed. I don't know what's inside it. Now it's easy because I see how these spins are organized, but in reality, I've just been given a black box, and inside it, there is a white square that I would like to image. So that's an important setup, because if you don't know what you don't know, you won't be able to, visualize the rest of the explanation. So I have just taken all of the spins in that inner square, and I have tipped them into the transverse plane. So this is the equivalent of DC, okay? I have just acquired the average value of all of the magnetization that is present inside the box. But that is not enough to know that inside I actually have a box. Instead, what I need to do is I need to be manipulating these magnetization vectors in different ways so that when combined, they will give me different patterns. And from those patterns, I will infer the shape of the object that is inside my black box. So what will I do? First, I will turn on an X gradient. An X gradient will make these spins over here precess slightly faster. These spins here at the center, they're still on resonance, so they will just stay fixed. And then these spins here will precess slightly slower. And because it's easier for me not to show the entire spinning, I will just show it as these moved a little bit clockwise and these moved a little bit counterclockwise. So what did I do now? Well, I created a pattern of magnetization, which is moving in the X direction. These spins are in the same phase, these spins are in the same phase, and these spins are in the same phase. So I have this kind of vertical variability. And then the next thing I will do is I will apply a Y gradient. Now a Y gradient will make these spin slightly faster, these will stay stationary, and these will spin slightly slower. So these will go clockwise, these will not move, and these will go counterclockwise. Okay? So you see, I turned off the X gradient and I turned on the Y gradient right here. Oops, I need to fix this part here. Y, sorry, let me just do this real quick, because if I don't do it now, I may just not get back to it. Okay, there you go, GY. Okay, so X gradient turned on, they have moved, Y gradient, and now I end up with a pattern that is diagonal, okay? So now I have variability that is in this direction. And now I have another way of exploring what is the structure inside this black box. Next, let me turn on the X gradient, but with the exact opposite polarity. Now I will make these here spin clockwise, these stay stationary, and these spin counterclockwise. There you go. And now I have gotten a variability in the Y direction. These here are in the same phase, these here are in the same phase, and these here are in the same phase. And finally, let me turn back the Y gradient, but now let's make these spin faster and these spin slower. And finally, I'm back to where I started. So you saw this once, you're going to see it a couple of more times. Each time I'll be adding a little bit more and more complexity. But for now, all I've done is I've just manipulated different parts of the box to process at different frequencies using gradients. How does that look in the Fourier space? Well, in the Fourier space, right now, I'm at the DC component. I'm just looking at how much average magnetization is there. And then when I turn on the X gradient, I will be exploring the frequencies that are along this line in the X direction. So gradient turns on, I'm over here, Y gradient turns on, I go up diagonal, turn it back on, and come back to where you started. So by manipulating the gradients, I can move this point anywhere in the Fourier space. So if I want to touch over here, I know that I need to turn the X gradient on and keep the Y gradient off. If I want to go over here, both the X and the Y gradient need to be turned on. What happens if I want to go over here? How do I reach this point in the Fourier space? A question for you. I think you'd be able to answer it. So I'm not looking at you, so I'm not sure how lost you are. But you see how basically turning on the gradients gets me to different positions. So let's go back. I'm at the beginning and I move to the right. So if I want to move to the left, what should I need to do? Okay, I'd
Isn't
really like
it-
to hear your thinking because, yeah, go ahead.
Yeah, sorry. Isn't it turning the gradient x, but in the counterpolar
Yeah, that's
direction,
exactly
right?
it. So how clear is it for everybody that, I could just do it in the opposite direction? Turn the x gradient negative, and then you're moving to the left. Turn the y gradient negative, and then you're moving down. Is that okay for everybody? Because it's pretty cool. Like this is actually a Nobel Prize. Okay, so you're gonna understand one very fundamental concept of how images are formed. Okay, so got a couple of hands up. I think everything is fine. I'll just keep going. Now, this equation here, we don't have time to do it. But it's probably one of the most complicated integrals that you've ever seen. This form here,
We don't
this
see.
basically is a basic Fourier transform expression. You have the magnetization vector, and you're taking the Fourier
Prof?
transform with respect to the variable k. Is there a question? Somebody said something?
Yeah, sorry. We can't see your slides now.
Sorry?
You're not sharing your slides.
Oh, I'm not sharing my slides. Sorry about that. Yeah. Okay, there you go. So this formula, that's a Fourier transform formula. You've seen it if you've done Fourier transforms. M, the thing that you're trying to take the Fourier transform of, to the complex exponential where you have two variables, k and x. However, your k is actually a function of the gradient. So rather than a simple variable, your variable kt is a function of the evolution of the gradient. And if you can make sense of that, then you really understand Fourier transforms. Because until now, probably the only thing you've done with Fourier transforms, you say, I have time and I want to move to frequency. Except what if your frequency is actually a function of the gradient, which is actually a function of the time? And in the end, everything gets written down as a function of time, even though you're taking the Fourier transform of a spatial variation. So it's really involved, it's really complex. I have no way of explaining that equation right now, but I do have one more demonstration that hopefully convinces you that this actually works. And this is how it looks. As I said, we're over here, we're just looking at DC, okay? What does DC look like? Well, it's just a single flat component. So we're here, the gradients haven't been turned on, but I can measure how much magnetization there is on average, and I can add that to my reconstruction right there. And then I can move to the right, just like I did before, except now I'm showing you where I am in K-space. I have explored this point in K-space. Let's see how much there is. I uncover it and I see, oh, there is this much of this Fourier component in this particular configuration. So let me just add it to the reconstruction. And now I've been able to explore the structure of this box, but only in the x direction. I really don't know what's happening in the y direction. But I already kind of know that it is limited in the x direction, that there's these black bands on the side, but inside, in the middle, it's pretty much a rectangular thing. But now I'm going to go up and I'm going to explore the diagonal component. How much of a diagonal component is there? Well, I take this value over here, I multiply it by this Fourier component, and I add it to the reconstruction. And this is starting to look more and more like a circle, not a perfect, more and more like a square. Not a perfect square, but we're kind of getting there. Let me move a little bit to the left. Now I want to explore how much of a y variation is there. Well, let's get this value and let's calculate the Fourier component, multiply it, and add it to the reconstruction. And now it looks slightly more like a square. So imagine that I have moved around and explored every single point here. If I do that, I add all of the components and I end up with a reconstruction of the square that I started with. So this may look anticlimactic, but I think I set it up well. You didn't know that that was a square. You just had a black box. And there was no way for you to infer what was inside it aside from exploring each frequency combination, adding it together in the reconstruction, and finally coming up with an image that looks like a square. But this will work with anything. You have a brain in there, nothing will change. You will still just create different patterns with your gradients and then calculate the Fourier components and add them to the reconstruction. So this is the way you make an image. Now, I think that this is really cool. which is why I had spent a month preparing these slides. I would love to answer questions because I know that the first time you see this, it may be a little bit disorienting. So give me feedback. What do people think? How many people are confused? Okay. Tell me what you would like to know. Again, I don't expect you to get all of this. Your case studies are not going to be about how you reconstruct Fourier transforms, but I want to get your feedback so I can do a better job of explaining it.
Yeah, so I think I missed the big picture of the thing, and I'm not sure
Okay. Okay.
why are you doing this?
Okay. So no slides, just hands. I have a black box. Somebody gives it to me. It says, what's inside this black box? Could be a head, right? I'm like, I have no idea. Okay. So I have this very powerful method that allows me to manipulate the magnetization inside that box. Now, assuming that inside that box there is something magnetizable, such as water, what I'm able to do is apply a gradient so that I can create different patterns of magnetization inside the water, right? So just like I said, make the left be slightly lower frequency, make the right be slightly higher frequency. Now what I'm doing is I'm saying, create a diagonal magnetization pattern inside my body, and then create a horizontal and a vertical pattern inside my body. And each time I create that pattern, I try to measure how much of that horizontal or vertical or diagonal magnetization is there inside my body. I take it, I put it all together, and because these are all two-dimensional frequencies, when I put all those together, overlap them one on top of each other, I end up with an image of what's inside. Did that make sense at a hand-waving level?
Yeah, a little bit more. I think I
Okay.
see.
Maybe other people can ask that, maybe I'll give a slightly different explanation. It's all about creating magnetic patterns in your body. Okay?
I have a question.
Mm-hmm.
So I was wondering if this is the conventional way of doing MRI now, like at present, or there are other innovative means.
It's pretty much the conventional way. I mean, you can modify slightly the order in which you acquire these points. Sometimes you don't need to acquire all of them. Sometimes you can be very fast in the center and not do anything on the surface. But in general, this is it. You're always generating patterns of magnetization.
I'm sorry, but I still think I didn't get the picture of it. So,
Okay.
like, what do we measure? Do we measure the induced electromagnetic field that we impose to our body, and
Yeah.
that is that it?
You're measuring, so you know that you have a magnetization vector in your body, right? The way that it's represented is it has just been tipped. Somebody just tipped it into the transverse plane. So you end up with these magnetization vectors that precess. Every time they precess, you collect the amount of signal. Because if you have a magnetic vector that is spinning and you have an antenna, you have a changing flux and that induces a current in your antenna. Okay, so that's the setup. And for now, just imagine that that never disappears. We know it does. That's why we have T2 decay and T1 recovery. But if it doesn't, all you're doing is you're acquiring a signal from many different locations in your body. Now, some of these are going to be pointing this way. Some of them are going to be pointing, how do you say it? This way, this way. So this antenna picks up a pattern of magnetizations that interfere with each other. Now, the antenna doesn't know that. As we showed, the antenna is just a one-dimensional signal. But you can know at every point, because you control the gradient, for which pattern we're talking about. So if the antenna says 100, you're like, oh, I have 100 of the diagonal component. And then the antenna says 50, and you say, oh, I have a 50 of the horizontal component. And the antenna says 1,000, and it says, oh, I have 1,000 of the DC component. Because I know exactly at which point in time how much of that component there is. That's the beauty, that my gradients actually take you through different patterns. And you know exactly which pattern is being explored at every point in time. So you can reverse engineer it. Your antenna will have a reading. That will be the coefficient that says that's how much of this pattern there is in this box. And if you get all the patterns, in a proper Fourier way, meaning obeying the sampling theorem and doing all of these Cartesian reconstructions and everything, you're able to put together those patterns together and form an image. Okay, so again, it's not the main point of MRI, but I really think it's fascinating because you've never seen the Fourier transform this way. And I mean, that's really the only reason I'm teaching you this. I'm not going to be making you read papers with reconstruction. How's everybody else doing? Is that making more sense now? Any other questions? You did understand a Nobel Prize in medicine, so congratulations. I think that's one thing you can put off your bucket list. You've understood one Nobel Prize. All right. So now things are getting a little bit simpler and we're about to take a break. I realize that this went on a little bit long, but these are just basic Fourier transform properties. And honestly, if you haven't seen Fourier transforms, it's not going to do you much good. But basically, you can manipulate these images. And, if you have something like this in one space, in the K space, it's going to look like a jink. We call this a circ. If you have two circs, or if you have a brain, this is what the patterns are going to look like. So these are the Fourier transforms on the right, and these are the original images on the left. You want to work with simple two-dimensional images. This guy here is Seiji Ogawa, the guy who invented functional MRI. You take a Fourier transform. This is what you get. You want to take a look at just the low frequencies of Seiji Ogawa. There it is. You want to take a look at the high frequencies of Seiji Ogawa. There it is. You want to try to sample different portions of the K-space. This is the entire K-space, so the full Fourier transform. This is when you only have half of the Fourier transform. This is when you only have a quarter of the Fourier transform. This is when you only have an eighth of the Fourier transform. So you see that this is a low-pass filter, and you're basically just getting the more slow variations in the image. You're not getting any of the high variations. You could also just try to preserve the high frequencies, in which case this is 7/8 of the image, this is 3/4 of the image, this is 1/2 of the image. You combine this and this, you get the full K-space. You combine this and this, just sum them up, you get the full K-space. You combine this and this, you get the full. So low pass, high pass, together. Low pass, high pass, together. Low pass, high pass, together. And you can cut images any way you want. This is just basic digital filtering. Also, if you want to mess with the resolution, you could just acquire bigger or smaller brains. All that requires is just acquiring the Fourier transform in slightly different ways. So to get the image to be much bigger, you will need to acquire all the way out in K-space. Whereas if you want to make the image smaller, you don't need as many frequencies. You will just acquire the center of the K-space. So these are all decisions that we make every day when we program an MRI scanner. What resolution do I want? What is the maximum spacing that I'm able to space out different neighboring body parts? And again, these are just simple slides that I wouldn't want to go into too much detail. If you've seen Fourier transforms, you know what I'm talking about. If not, you just believe me that this is how we do it. And finally, this is an artifact that happens in MRI a lot. So basically, I'm acquiring a brain, and all of a sudden, I get this stripe pattern across it. And this stripe pattern, can anybody tell me what it is due to?
It could be like a parasite RF impulsion or something.
Yeah, exactly. I think that's Sandrine, right? Because she's seen that. So it is true. Often it is caused by just opening and closing a door of the MRI scanner, okay? And it turns out you do that at a specific point in time. So what does the artifact in the Fourier transform space look like? Like, can you tell me what the Fourier transform will look like if this is the Fourier transform of a normal brain?
It can be just like one point.
Exactly. It's just a point here. As we were passing through that point with our gradients, somebody opened a door or somebody created some kind of parasitic interference that is giving us a false signal. So in MRI, you see this a lot. And fortunately for this one, you just set that value to 0, and then the image is going to be back to normal. It's not always that simple, but this kind of artifact is very common because every time something happens as an impulse, you will see it as a pattern over your image. And I think
have a
that's,
question.
yeah, go ahead.
How would you correct images that have artifacts in them?
Right. So, I mean, there's different ways. Sometimes you just deal with the artifacts. Like sometimes the artifacts are just inherent and you will just leave them inside because there's not much you can do. For example, if you have certain spiral trajectories, your artifacts will look like a little bit twisted brains, okay? And there's not much you can do about that. But often what you do is you try to acquire in ways that preserve some sanity. For example, for this artifact, you know that if you have a real image, the Fourier transform needs to be symmetric. It needs to be, what's the word? Pair in French. It needs to be even in English, okay? So this is not an even Fourier transform, that's a sanity check. You know you have a problem. So there's kind of like error correction codes, right? You know that certain things need to be this way, and if they're not, there's a problem in the data that you've acquired. Okay? So let's leave it at that, and let's take a break until 2:30. And then I will talk to you a little bit more about the topic of your case study, which is a little bit more specific, and we'll have time to explore those topics next week. So 12-minute break starting now.